So welcome to the talk about cinematic lighting in Unreal Engine. So I'm Jerome Plateau, and today we're going to get an in-depth view of a next-gen experimental lighting and rendering technique in Unreal Engine. So this is a project that is in collaboration with ILMxLAB and NVIDIA. So real-time rendering has been improving over the years. The type of technique available are limited by the current hardware and API. So what can you do if some of those restrictions are lifted? So today we're going to have a kind of a glimpse into the future of the real-time rendering. So it's a prototype that is powered by the NVIDIA RTX technology using the Microsoft DXR API. So this API allows experimentation with both hybrid and full ray trace method. So we did a lot of experimentation. Not everything turned out great, but we want to talk about them anyway. So let's take a look at all the new technique that we have in Unreal Engine. So we have the new texture area light that help us to shape the light. So we use an HDR image to actually texture the light. And then now we have also ray traced area light shadow. So as you can see, when you change the size of the light, the penumbra of the shadow looks different. It's a lot softer. And everything is, of course, rendered in real time and fully dynamic. So we also ray trace the ambient occlusion, so that helps to ground the character a lot more. And then the best way to show ray tracing is actually to show ray trace reflection. So Phasma is probably the best character for that. And as you can see, the environment is updating in the reflection. We also improved the depth of field, so we call it cinematic depth of field. Again, the environment updating in the torso, as you can see. And then NVIDIA has been working on a lot of denoising algorithm. So now we can afford some sort of a glossy reflection. And it's great to see that you can have some interactive reflection. You can see Phasma and the Stormtrooper in the elevator in the reflection in the chrome sphere. So with all that put together, we decided to create a smaller piece of cinematic with that.
What's the story with all the elevators lately? I heard Kylo Ren destroyed the one over in D sector. If you ask me, who's ever in charge of this place should be transferred to Hoth. What? Oh. You think she heard us? Yeah, I think she heard us. At least we blend in for once.
So to talk about that, I would like to introduce Ignacio, who's going to talk a bit more about the techniques.
Thank you, Jerome. Hi, my name is Ignacio Llamas. I work at NVIDIA on real-time rendering. And I'm going to tell you a little bit about the API that we use to implement all the technology that uses ray tracing in this demo. It's called DirectX ray tracing, and we use this to take advantage of NVIDIA's RTX technology for ray tracing. It's a new ray tracing API that will be extended in DirectX 12. It exposes a flexible and programmable programming model. And it's also IHV agnostic, which is very important for developers so that they can use this API on any IHV hardware that supports it. DirectX ray tracing exposes NVIDIA RTX ray tracing technology on Volta GPUs. It provides a programming model that is similar to NVIDIA's Objects API programming model, and provides a new type of pipeline similar to how we've had for many years a rasterization pipeline or a compute pipeline, and we call this a ray tracing pipeline. This pipeline provides 5 new types of shaders for ray tracing, which we call ray generation, intersection, any hit, closest hit, and miss shader. Let me tell you a little bit more about this pipeline. Here, there's a diagram on the right side where we depict the basic flow of how the pipeline works. On the top, we have the ray generation shader, which is the starting point. And this shader, along with the miss and closest hit shader, have a new capability to call a new type of built-in function called trace ray. When you call trace ray in your shader, the implementation will provide all the functionality to traverse an acceleration structure that is opaque. And as this acceleration structure is traversed, we may need to run or execute some shaders to compute intersections with custom types of primitives, or optionally also after that, what we call the any hit shader, which is useful, for example, to implement alpha test or alpha masking. After the traversal completes, we will have either found a hit that is the closest or not. If we do, we invoke the closest hit shader, otherwise we invoke a miss shader. Okay. In addition, it's very important to note that the calling shaders that call trace ray have the ability to do this many times, and they can get return values from the call, and these are obtained through a mechanism we call a payload, which is an application-defined data structure that is readable and writable by the different shaders. So it can be used as input and output. Ray generation is invoked similar to a compute shader. The application dispatches a new type of dispatch call on the command queue that launches a 2-degree of ray generation shader invocations. However, unlike compute, there are no thread groups and therefore no barriers across these threads at a finer grain. Ray intersection is enabled in the API by both built-in support for intersection against triangles, and also using custom intersection shaders that are basically shader code that you can write to enable intersection against any type of geometric primitive, such as sign distance fields, sparse volumetric data sets, subdivision surfaces, or height fields, for example. All of them along the same ray that would be trying to intersect triangle geometry. However, there is no payload access in the intersection shader. The any hit shader has the capability of ignoring hits or terminating the traversal. However, it cannot generate additional rays. It cannot call trace ray, but it can modify the payload. And one important thing is the traversal order is not guaranteed in the any hit shader. It may be called in not exactly in the ray parametric order in which the hits are found. The closest hit and miss shaders are very similar in functionality. The only difference is one is called, a closest hit shader is called if a closest hit is actually found, and a miss shader is invoked if none is found. All of these, in both cases, can happen after some number of any hit shader invocations and intersection shaders happen during traversal. And importantly, as I mentioned, both of these type of shaders can call trace ray, which means that we support trace recursion up to some level of recursion, and they can read and write the payload. And finally, I would like to tell you a bit about the acceleration structures on which the ray tracing traversal and intersection happen. The API supports 2 levels of acceleration structure. A top level that contains at the leaves instance nodes pointing to bottom level acceleration structures with a transfer matrix, and a bottom level type of acceleration structure which is built over geometry, which can be either triangles or axis aligned bounding boxes in the case of geometry using custom intersection shaders. We support also 2 types of acceleration structure commands. One is to do a full build, and the other to do an update, which is a lot faster. And it's really, really important to enable deformable triangle geometry in real time. Also, I would like to point you to Microsoft's talk later today at 3:30 p.m., where they will go in more depth into the future of DirectX, including DirectX ray tracing, and their blog in that link. Now I'd like to tell you a bit about reflections. as in the technique or the rendering effect, not the title of the demo. Reflections are one of the more key promises of ray tracing, and it is a relatively hard problem to achieve or solve correctly in rasterization-based techniques, in dynamic sense especially. It is easier with ray tracing, but it's still quite expensive because now instead of shading just the primary hits or what you see from the camera, you also have to hit what is reflected. You have to shade that and light it the same way, and potentially for multiple bounces if you want something really realistic. So it's a lot more shading work as well, not just ray tracing. Here is a shot of the character Phasma in the demo with interreflections. With the current ray budgets, we decided to limit ourselves to 2 bounces in this demo. It's still the most expensive part of the frame. So we had a few ideas to attack the problem and improve performance. One, the first idea was simplifying the shading of the materials for reflection shading. Another was to adaptively do more or less bounces. And the third was to use sophisticated denoising techniques so that we could actually get the glossy reflection looks in the glossy materials. So in a bit more detail, we simplified the materials by providing the artist a new type of node in the material graph editor, where the artist can define a subgraph for a simplified version of the material. This is very useful because the materials used in this demo are really movie quality. They have a lot of micro detail, and that micro detail is not usually appreciated in reflections that are either glossy or that are minimized or minified by the fact that the surfaces are curved. The second approach that we took to reduce some of the cost was to only trace secondary bounces when the roughness was above a certain threshold. This reduces the work in some scenes. While many bounces is expensive, and in the demo we limited ourselves to 2, we can actually use many bounces in other scenes, like this one, which is a slightly modified elevator with 2 mirror worlds. This one was running with 40 bounces, and it still runs really well in real time. Finally, we use sophisticated denoising developed by Edward Liu at NVIDIA to provide the glossy reflection look that we needed with just 1 sample per pixel. And this also relies on a slightly customized temporal anti-aliasing pass in the Unreal Engine, which we execute before applying the denoiser. We will provide more details on this about this in our talk at 12:45. Here's just an image showing you a little bit what the denoiser is capable of. On the left side, you can see what we obtain with 1 sample per pixel, which is a very noisy reflection. In the middle is the reference achieved by accumulating 1,000 samples per pixel, and on the right is what we achieve with 1 sample per pixel plus denoising. And with that, I would like to hand over to Marcus, who will talk about area lights and indirect lighting. Thank you.
Yeah, so we talked about reflections, and I'll tell you guys a little bit about some other features that we implemented, specifically rectangular area lights and some indirect lighting techniques. All right. So rectangular area lights was a key ask from our content creators. Like, at the very beginning of the project, when we started doing this, we talked to our art team, and people with cinematic backgrounds like Jerome really expect to be able to light scenes with real physical lights with a size so that they can get nice fall off for the shadows and a nice light shape. So this is something we knew we really wanted to do. On previous demos, we would emulate this effect with kind of like a 2D grid of mini lights, which works pretty well. You can see it in the Fortnite trailer from last year, but it's kind of a pain to set up, and it can be quite expensive depending on how many you add in. So we handed the problem over to our resident area light expert, Brian Karras, to implement a solution. And we came up with one that does an analytical closed-form solution for diffuse and specular, and leaving the ray trace budget for the shadowing, and then also using texturing to modulate the light emission. So let's take a quick look. So this is what you would get with a traditional rasterized point light shadow. You can see that the shadows are pretty high quality and not aliasing, but they are quite hard shadows along the whole length of the thing. So if you would increase the size of the light, with a ray trace shadow, you get something more akin to what you'd have in the actual real world, where the contact point close to the object is hard, and then you get a nice soft fall off as you move away. And then, of course, the larger you make the size of the light, the softer your shadow gets, which is quite helpful when lighting scenes. All right, so kind of how does it work? It's based, the analytical portion is splitting the lighting and visibility integrals. So the lighting is done at a higher variance at high dynamic range, and the visibility is done at a lower variance with low dynamic range. The unshadowed portion of the integral is calculated at the sample point analytically, and it's based on linearly transformed cosines with no noise. If you want some really deep technical details on this, this work was based on some work presented by Eric Heitz et al. Back in 2016 at SIGGRAPH, and I would refer you to their excellent paper for a real deep dive into that method. So the good news is that the unshadowed version of this technique will be available to the standard UE4 deferred renderer in 4.20, and that includes some new, faster approximations, more suitable for games, and some improved sphere and capsule area light that Brian tacked on as a bonus. All right, so let's talk about the actual shadowing portion, which is using the ray tracing. So there's really no good rasterized solution for this kind of effect. Like I said, you can keep the grid or whatever. In our case, we had a limited ray budget, about 1 ray per pixel per frame per light. It's important to note that the cost of the technique goes up with the size of the light area as your ray coherency decreases. One key effect is like the more coherent your rays are, the more performant they are. And because you only do 1 ray per pixel, as you can imagine, you might get a pretty noisy result. So let's take a look at the raw unfiltered. I don't know if you can see on the screen there. It's pretty good. So it's pretty noisy. All the shadows are in the right place, but it's not really the look you want. So what are we going to do about it? We apply some denoising. So our friends at NVIDIA have been researching sophisticated denoising techniques for quite some time. They've done quite a few presentations over the last few years. So Ed Liu from NVIDIA adapted these techniques for shadow denoising for our demo. He will be talking, I think, with Ignacio later today, if you want to swing by that same talk. But if you look at the result, you can see it's nice and clean. If you would go back and watch the video, you can see that even in motion, it holds up very, very well. And this lets you get away with quite a small ray budget with still a good look. There we go. And then the final piece of the rectangular area lights is texturing. Your lighter wants to light the scene with not a solid emission intensity across the entire face of the light, so this lets them have some more complex light shape. So this technique is not ray traced. Again, it's a pre-filtered integral to avoid Monte Carlo integration and noise that you would get. It's also very fast because you can do it with a single texture sample with some MIP level picking based on roughness to get the appropriate blurriness. And this portion as well will be coming to stock UE4 and 420 with the full area light package. Okay, so quick look at what that looks like. So you get the nice kind of textured specular area in the kind of glossy floor there with the Ampere symbol. It's kind of a cool show off of the technique. Okay, so the next portion I want to talk about is kind of ambient and indirect lighting, which Patrick Kelly worked pretty hard on. So these two techniques are pretty key to creating believable scenes. You really want your objects to be grounded in the scene to make sure that they really fit in. And we have pretty good solutions for static environments for games. So, you have an unmoving environment, and all the time in the world, offline, you can pre-calculate all kinds of data. That's really helpful to make these look correct. But it's traditionally difficult to calculate properly for dynamic objects. We have pretty good approximations, standard techniques like screen space AO, baking out spherical harmonic light probes, baked AO textures, volumetric light maps, et cetera, et cetera. But let's take a look at some of the artifacting you might be familiar with. So this is a bit exaggerated for effect. So this is standard SSAO. You can see the kind of the haloing around the character next to the wall, and on the body of the gun. It's not quite physically correct. Yeah, I also want to note that for this slide and the upcoming slides, we've removed all the direct lighting and shadowing, so we're just looking at indirect here so that we can really appreciate what we're talking about. So again, this is SSAO. We're going to use this shot to do some further comparisons. So we don't have the giant halo on the wall, but still some across the body. And in a traditional game, people would tweak the shot to look a little nicer, but we're just trying to show off the effect. All right. So when you have ray tracing, this provides the opportunity for us to sample the full current state of the scene, including the dynamic objects, for better approximations. We're not just limited to, say the depth buffer like we are for screen space effects, or just our pre-calculated offline static data. So with this, a little diagram of kind of how the ray traced AO works. Like if we're shading the point P there, you want to fire off AO rays in the hemisphere. Across the normal of the surface, because you don't really care about what's going on behind. You can be pretty sure that's occluded. And then you only want to go out to a certain maximum distance because, when you're applying AO, you don't really care about things that are, a kilometer away or anything. So depending on how many rays you can afford, you fire them off in, like a random Monte Carlo pattern, and you see how many hit, and then you can shadow off your AO. So to do this, we can use the programmable ray gen shader to generate the occlusion rays. This lets you, control your randomization function and find something that works. We have a cosine-weighted hemispherical distribution, and it usually requires quite a few rays to converge. We found in testing that if you had about 16 rays per pixel, you got a nice result. This was too expensive, though, and we ended up allocating a budget of 2 rays per pixel, which you might imagine looks a little noisy. So again, all the AO is in the right place, but we're just missing some data due to the low sample rate. So the solution is very similar to what you saw before for shadows, which is let's add some denoising. So again, we had NVIDIA go through and adapt some of their techniques, and you definitely get a nicer result. But in the end, you still are really only dealing with a very small amount of data. There's really only so much you can do with it. So to fix that, we apply another standard UE4 technique, which is TAA. So TAA allows you to, with reprojection and your 2 samples per frame, kind of go over and accumulate the amount of data that you really want. In our case, like the 16 samples per pixel target that we wanted. So over a couple of frames, you can accumulate that, and with the denoising, you get a really clean result, as you can see there. However, there is a problem with TAA, and that problem is shot transitions. So whenever we do a camera cut, we basically lose all the history that we'd been accumulating. It's no longer valid. So without a history buffer, you're back to just your original 2 samples from the current frame. So in this case, we tend to prefer overblurring, like we're not generating the data, so we have to deal with what we have. So in this case, we can substitute our maximum AO hit distance into the filter kernel, and essentially we just blur out wider and then shrink the kernel back down again as we accumulate up to our target data rate. So you can see kind of what the original state looks like. So this one was particularly bad. They're not all quite this bad on the camera cut. And this is even the denoised version. You can see it's quite still quite noisy. So with the adaptive kernel, you get something that looks like this. It's not so objectionable. And remember that over the course of the next 5 or 6 frames, this converges on the actual result you want, and it's much less distracting during a camera cut. In fact, you're probably not going to notice it unless you're looking for it. All right. So let's talk about some other indirect lighting. We've got the ray tracing, and one of the dreams of real-time rendering is, of course, dynamic GI. So we thought, well, let's try out something to see if we can get some bounce GI from this thing. We wanted to try to use the ray tracing seed data and then add in some data from our offline acceleration structures to see if we could come up with a fast approximation that might give us some stronger directional influence and maybe some extra bounce from the dynamic objects, because the troopers are pretty white. They bounce some light around the scene. So another little diagram. So the yellow dashed lines are the cells in our volumetric light map structure, and we're shading the point P. So you want to fire off some indirect bounce rays to see if you hit anything relatively close by. In this case, the surface on the left. And then you will want to fire off some visibility rays, similar to AO in that case, to see just how much of that surface is visible to the original surface to calculate the proper light transfer. And because we can evaluate the material and the full lighting at the point P, we can calculate a pretty good light transfer function. So what does that look like? So in this slide, we've removed all other lighting except for just the bounce calculation. And you can see you get definitely more directionality out of the volumetric light maps than you would otherwise, and there's a little bit of extra bounce lighting under the chin off the armor that kind of helps sell the indirect. So this is without that. This is just the RTAO times the standard UE4 volumetric light map data, and then with the extra bounce, you get something closer to what you would get with an offline bake. All right. So unfortunately, you did not see that technique in the cinematic we played earlier today. We found during experimentation that it kind of requires a ray budget of around 16 samples per pixel, even with the denoising to look good. But I did think it was important to talk about because I think it's a good inspiration for future work and an example of how you can experiment with the new techniques and the new data we have to create real-time techniques. And then last but not least, you may have noticed that we have a brand new cinematic depth of field that Guillaume Abady's been quite hard at work on the last few months. So this is a brand new implementation for depth of field for UE4. We've designed it to scale down to lower hardware, and this is meant to replace all existing methods of depth of field in UE4. I don't know if many of you are familiar with them, but I think we have 3 of them right now. So it's a configurable procedural diaphragm simulation of the camera, so you can change the number of blades, the curvature of the blades, and we also have vastly improved bokeh quality and much improved transitions between foreground, background, into the focus areas. It's also much, much faster than our existing techniques. So let's take a quick look at a beauty shot there. So you can see the nice pentagonal bokeh on the lights in the background, and maybe if you download the slides later today, take a close look. But the transition between the near out of focus towards the back of the shot is really, really good now. All right. So that's it for features. It's time to hand it over to Arne Schober, one of our senior rendering engineers, to talk about performance.
Thank you, Marcus. So with all those expensive technologies in place, let's talk a little bit about performance. As you might know, real-time is a key for Unreal Engine 4 and Epic Games. Therefore, we set a conservative goal of 24 FPS at 1080p for this piece. This is usually much more generous than a normal game's budget. But let's have a look with the initial results on the Titan V. As you can see here, we had 140 milliseconds on a single GPU in the worst shots, which is about 3 times of the budget we had. So what are the solutions we can look at? As we did not want to sacrifice any quality, and we knew that simple optimization just would not suffice. So the solution to that was, just let's paralyze all the things, throw more GPUs at it. Thankfully, NVIDIA provided us with a new DGX station, which consists of 4 water-cooled Tesla V100 GPUs and a 4-way NVLink GPU interconnect, which is about a magnitude faster than what you can get on PCIe today. However, there's no multi-GPU support in DX12 for Unreal Engine 4. But thankfully, Uriel and Matthew collaborated with Walt Disney Imagineering and implemented RHI support for mGPU officially now in Unreal Engine. You can now create objects on different devices with GPU masking, execute the command list on different devices as well. You can use mGPU fencing to synchronize your workloads, and all of this will roll out in 420 and 421. But remember, this is not a turnkey solution yet, but it provides you with a stable framework to experiment easily and reliably. So let's look how the work can be distributed. We tried many, many things. One of them was alternate frame rendering, where every nth frame is rendered on a different GPU. For that, you need to copy or directly read the temporal data over NVLink, which is extremely fast. But this would increase the input latency for our games, and it would be also difficult to integrate with the editor. Another option we looked at was SFR, split frame rendering, where you can either have fixed quadrant locations for each GPUs, or you have some sort of a checkerboard pattern, or you can either copy the data over to the primary GPU or directly read it, write it to there. What is very important for us is to have great profiling tools. Those are invaluable to understand what is going on. And thankfully, to Yuri, who implemented a new profiler frontend in Google Chrome tracing, we could see what's going on in our frames. Here you can see AFR in a simple scene, and you can see where the presents are happening, and they're kind of a little bit staggered together. So although you have twice as much frames per second, it will still feel a little bit choppy due to the microstutter. So let's look how SFR can be used to divide the ray tracing work. Here you can see that the primary GPU on the right does all the denoising and post-processing, and the rasterization is duplicated on all devices. All the ray tracing work is distributed on all the 4 GPUs. But based on that ray tracing work, we had only between 60 and 90% of parallelizable workload, which, according to Amdahl's law, gives you a maximum speedup of 2.2 times on 4 devices. But thankfully, Evan Hart came up with a better implementation. Here, the primary GPU only runs the expensive full-screen effect and shadowing. The rasterization is still duplicated, and the other three helper GPUs will distribute the ray tracing work amongst each other. They also run half a frame ahead so that they can nicely overlap with the denoising and post-processing. So what are the takeaways? Good tools are very, very important. And as of now, multi-GPU is still a little bit labor-intensive to get to work right. And one has to try a lot of things and experiment what works in your scenes and what doesn't. But when you finally see the results, they are really, really impressive. Let's have a look at the performance again. So this is how we started on a single device, 140 milliseconds. And after throwing more GPUs at it, we were there in budget with a few minor drops. So finally, let's hand it back over to Jerome, who can tell you how to put all this awesome technology to good use.
Thank you, Arne. So let's talk about content a little bit. So okay, to give you an idea, the Stormtrooper were roughly above 500,000 triangles, which is 300,000 vertices. So the idea with this demo is to have as much detail in the model inside the engine and not use normal map, or at most, almost none. So the only place we actually use normal map were the pieces of rubber between the armor. The rest has been modeled and is in the engine to take advantage of all the ray tracing feature. For the texture, or for the shader in general, we didn't pay too much attention at optimizing the materiality. We knew that there would be not more than 3 to 4 characters on the screen. So we know that on the CPU side, with all those extra draw call, it would not be too bad. But we pay attention to stay pretty conservative on the texture side, so we use a lot of tile maps, as you can see at the bottom. And then the only few maps that were pretty big were the ID maps, just to get the nice shader transition between all those different materials. And then for the environment, it was kind of like roughly 2 million triangle total, which is a 750 draw call total. So even in all the shots, we never see the full environment at the same time. So even, again, on this side, it would not be too big of a deal. And then, of course, we try to make those demos as realistic as possible. So we use image-based lighting to do all the look dev, and we make sure all our shaders are as physically correct as possible. and we test all those material against different lighting scenario. And then, as Ignacio was mentioning earlier, we have two shaders. So we have the complex shader that is actually visible on screen, where you can see all the detail. So we have the scratch, you have the dirt map, and all those extra like micro detail and normal map. And then we have the simplified version of that look dev. So that simplified shader is actually used for the ray trace bonds shader. And then for the lighting setup, so since the beginning, we knew that it would be kind of a hybrid of traditional techniques and ray trace technique. And we wanted to keep the ray budget as on the dynamic object, so all the characters. And for the environment, we kept the classic baked lighting. So, whoops. And then to bake the environment, we utilize the new area light. So the new area lights are actually working also at baking time, and this feature will be available in 420. And then for inside of the elevator, we knew that there would be a lot of character moving in and out, so we wanted to keep that part very dynamic. So we use a stationary light using also ray trace shadow. And then for the moving lights on the side, so we knew that the budget would be not more than 2 dynamic lights on screen at the same time. So we alternate those 2 lights once after each other. So no more than 2 at the same time. So we have, again, the stationary light on the top, and then one of those 2 lights on screen. And then for the bloom, so we use the fast Fourier transform image-based convolution, so we call it the FFT bloom, it's just faster. And then, so the idea with that bloom is to utilize an HDR map to define the shape and the look of our bloom. And then on top of each of the final render, we actually put some sort of lens flare, just to get that more cinematic feeling, and then kind of like that JJ lens flare that we try to get. And then again, the sequencer, classic, we use the shot manager to create all our shots and put all the information in each shot, and also for editing, so, and also creating those cue sound, like triggering those cue sound. But we use it for also something else. So as you can see here, it's Gavin, our director of the piece. And then, so we use the sequence recorder on stage to actually record each performance and then replay it back. So Gavin was able to actually jump into Phasma's suit and then play her, and then jump into a stormtrooper and see her in VR and react to her. So it was a great way for us to actually iterate really fast and then find the right pacing of the piece. And then because he was in VR, he was also capable of placing himself correctly and react again at the same, to the performance of the other stormtrooper. So it was a great way for us to improve our virtual pipeline. And then once that has been done and approved by Lucasfilm, then we move on with the classic motion capture with actors. So we would like to thank everybody, our friends at NVIDIA, and then our friends at ILMxLAB, and then all the people at Epic who worked on that piece. If you guys have any question, since we started a little bit late, we will be in the lobby later, and then you can come and see us. Thank you, everybody.